Thank you, Stephen. Some time for questions on both these papers. Wolf. Yes.
Yeah, I have a question to Dr. Ingustio. You alluded to the increased speed of quantum computing and the enormous storage capacity, and you referred to the natural computing systems, the brain, which is surprisingly fast given the slowness of the components. Now, it appears that the brain is using analog computing strategies mostly. And sorry?
Can you repeat the last sentence?
The last sentence. There is increasing evidence that the brain doesn't use the strategy of digital computers, but it's working like an analog computer. And is the idea you wanted to convey that the future computing will be more in the analog domain, the next generation of computers, the quantum computers, or is that also digital? Because we believe in biology that nature has gone the analog way to solve a lot of problems.
Well, I'm not a specialist of course, of biology, but here the idea is that in the way of our brain works, there is some mystery because, as I said, there is a speed and an energy consumption which is that we cannot understand because it's totally different. So in addition to, of course, the imagination, the creativity and so on, this is a real difference between our biological computer and the supercomputers and so on. Now, a new field of quantum or quantum bio has started to try to understand how it's possible that in our brain, where there is a strong decoherence time, because you know the temperature is room temperature, there is noise, I mean, and so on, so should not work so fast. So people are trying to understand why instead is so fast. And a possible idea is there must be some probably correlation between different, portions of neurons, I mean, and so on. So this is still a mystery. I must say that there are much efforts all around the world to understand this. And the idea is that if we try to understand the correlations which are among the different, neutrons which are maybe fast apart, maybe we can understand the trick and then use again the model, to develop a new computer which is anthropomorphic. Now, of course, this is something that, we don't know. For sure, to prepare my talk, probably I've been, to give the talk, I used something like, 20 watts or something like the energy of a lamp or so on. But if we do, should I try to do this thinking with a supercomputer, it would be billions of times more consuming energy. So it's a new field, a new landscape.
Thank you. Next question here.
Well, very nice talk, Massimo. My question is, do you believe, if I take Feynman notes correctly, that nature is not classical, and if you want to understand, you better do simulation in a quantum way? Do you think that really to understand the quantum phenomena, we need quantum processing? Okay, well, to really understand quantum phenomena, we need to do quantum processing. So there are things that we only going to understand if you are able to do quantum computation.
I think that the fantasy, the insight of this all the human brain has been able to think of schemes after the sentence of Feynman. Scientists went deeper and deeper in trying to understand the story of entanglement and these mysteries of quantum mechanics. So I think personally that using quantum mechanics, the laws of quantum mechanics, we can create this quantum simulator. Why quantum simulator? Because the moment in which you put atoms at the short distance, you create a crystal. I mean, like essentially we can see what's happened. So we cannot compute, I don't know, an high temperature superconductor, but we can probably simulate it and see how it goes.
Okay, well.
But then let me tell also another story. Another message is the following, that science develops technology, and with technology, you again go back to science, so who knows?
Okay. Now, I have a very short question to Professor Benner. When we, 4.6 billion years ago, I guess we had an environment with cosmic rays and everything that was a little different from today. So how valid is to infer about molecular formation without the presence of such energetic photons coming around? And
Oh, well, no, I mean, this is only part of the story, of course. The high atmosphere is very much bombarded with high energy photons, and that's a lot of the way you get from dinitrogen, carbon dioxide, methane, and so on to formaldehyde. And so the formation of cyanoacetylene, for example, HCCCN, is by photochemistry of into methane atmospheres, about 9–10% material.
yeah, but you need only UV photons, right?
Well, they're yes,
What
and
about
some
the
of them are quite
cosmic
hard.
rays and?
Right, now keep in mind the minute you have a reducing atmosphere, you begin to get the photochemistry like you have on Titan. So you get hazes. So it's actually quite hard to get hard photons down to the surface of that atmosphere. Now, a lot of this is inference, right? You have examples like Titan, but Titan is not Earth, right? And you have model-forming people who talk about planetary accretion and talk about what the compositions of these are. And we have, of course, statite meteorites, which are, of course, representing late arrivals to our Earth of what was the primary mass that created the Earth. But yeah, so the answer is we've got lots and lots of photons, and almost all of the reduced compounds that we mentioned that are important for nuclear bases are coming from those. In the higher atmosphere, probably not at the ground.
Question over there and then there.
I infer from your presentation that you favor the dry lands or wet surfaces on dry land perhaps as the most likely scenario for the origin of life. And I
Yes.
also want to take this opportunity to ask you your opinion about this scenario called the hydrothermal vents of the lost city type,
Yeah.
which seems to me very attractive.
Yes, the answer to your question is in a word, yes. There is what's called the water paradox, which I did not talk about, but it's that RNA really only works in water, but water destroys RNA. So, and you are surviving because you are using energy from your breakfast to repair all the damage that the corrosive water is doing in your body. So the answer is yes, we don't, we require dry land, and we are not advocates of the hydrothermal vent system. But if you had invited Mike Russell, you could have gotten a different story.
It was a very interesting talk and very entertaining as always. I have a question. When you come to the end, how the current view reconciles the old Miller-Urey experiment that comes from my UCSD years, remembers?
Well, the Miller-Urey experiment is a methane ammonia atmosphere as opposed to a methane hydrogen dinitrogen. There you go. Yeah, so it's a different atmosphere that Miller and Urey used, and of course what Miller and Urey did was get amino acids. That was their primary product. They did not get any carbohydrates at all. And so, I mean, you got to keep in mind that the foundational experiment in this field is the Miller-Urey experiment from 65 years ago, but a lot has happened since then, and one of the things that's happened is our concept of what the atmospheres could have been like have changed. Miller had no rocks, no minerals, nothing coming from the planet in that experiment. So there was no sulfur dioxide, there was no redox.
So if you do the experiment in vitro today, then will be a successful new Miller-Urey experiment?
Right, so what really would be necessary to persuade many people in the community, perhaps even myself, would be that you would have to set up a room maybe this size, where you had volcanoes down below putting out certain kinds of things, light from above putting in certain kinds of things. There are other ways of doing this, right? On Mars, we actually can find the borate minerals that we discovered as being important for formation of phosphate derivatives. And we do expect that there will be on Mars a lot of this basic chemistry up front also taking place, as you should be able to find these carbohydrate reservoirs on Mars as well. But yeah, I mean, there's just the, this is the Tom Wolfe line, no bucks, no Buck Rogers. If you want to try to get somebody to fund you building a room this size that simulates the Hadean Earth with volcanoes and atmosphere and all the rest of it, it's a hard sell.
Yeah.
You seem to make a fundamental distinction between the scientific method and natural history.
Yes.
Now, I think that's a false opposition that probably goes back to people like Ernest Rutherford, who is reputed to have said that there is physics and there is stamp collecting. Now, I don't think that's a correct way of cutting out things. I think natural history is fully compatible, or the scientific method is fully applicable to, or scientific methods are fully applicable to natural history, so long, I think there's one condition that must be met, namely that history leaves a trace. And that is the case if you look at biotic evolution. The evolutionary history, the phylogenetic origins of taxa, they leave a trace, they leave adaptive traits, and of course DNA sequence homologies that can be used to reconstruct the history of these organisms, the history of evolution. Now my question is, in the case of prebiotic evolution or chemical evolution or whatnot, what sort of traces do these historic processes that took place long in the past, what traces do they leave that we could use today to reconstruct that history, just like taxonomists use DNA homologies in order to reconstruct the evolution of biological taxa?
No, I'm going to defer to you as the expert in what is the scientific method. We define the mission of my research foundation as sitting between natural history and the physical sciences. And I must say that though I'm trained in the physical sciences, I don't see, when you look at standards of proof, standards of tenure and promotion, all sorts of things, it's very hard to actually find commonality between the way natural historians go about their business and a good physical scientist does. But you're right, all that we do, so in the sense that we are talking about an event at 4.36 billion years, which we cannot revisit directly, we do have to rely on traces. And we talked about a number of them. Those zircon crystals are really important to this argument because there are few other minerals that will survive intact for that period of time. But it's in those zircon minerals that you look at oxygen 16, 18 isotopes, clay inclusions, cerium-3, cerium-4 ratios, and all of that is leaving the trace of the rocks at that time. And of course, the chemicals, very little has been left, but there's 4.1 billion year old carbon in those zircons, which is indicating not only a biosphere, but widespread biosphere. And so you have 250 million years, not a lot, not a little, but enough time to go from that origin of Darwinism at 4.36 to the 4.1 biosphere. So those are all traces, and that's how we build the entire argument. But we do not go back and run the experiment that I was just alluding to, which is an organic chemist, how I'm trained, how you really should do science correctly. But the natural historians among my friends hate me for saying that.
I want to ask you, what is in this methodology the idea of the distinction between life and non-life?
Oh dear. Well, shall we turn this over to the group? The short answer to this is that life is a self-sustaining chemical system capable of Darwinian evolution, and what distinguishes an assembly of organic molecules that is animate from one that is animate is the access to random variation that's inheritable with errors where the errors themselves are inheritable. Now, inheritance is easy to get. You get it by growing crystals. Crystals have errors in them, so you can have defects in crystals, but the defects themselves are not replicable. So the hard part in getting life out of non-life is getting not reproduction with errors, that's easy, but reproduction with reproducible errors, that's hard. But that's what we say. And if you don't like it, you're welcome to argue, because I'll tell you that argument has gone on forever.
Yes, question there. Yeah.
Right, so it's self-sustaining, meaning it still has to eat, but it's able to find its own. So for example, when on the right-hand triangle on my last slide, we have created artificial chemical systems that are capable of Darwinian evolution. We don't make them self-sustaining because I don't want to have to deal with the Homeland Security Office saying that I have created something that can go out, evolve, and find its own food. But that's what we say. So the distinction is the ability to replicate with errors where the errors themselves are replicable, and that's the mechanism by which an organic system can acquire its resources in greater amounts from its environment, improve itself, and create the properties or the attributes that we value in life. That's the story.
Yeah. I'd like to address my question to Dr. Steve Benner. Actually, at the last part of your talk, you said about application, actually. So according to protein evolution, you successfully synthesized ancient protein to check the function. Apparently, this is a kind of like a new protein, or I mean, it might be very good for industrial application too. This chemical evolution, RNA world, and do you see what kind of application possible? Of course, you know, it's a possibility. This is a kind of a transforming role of basic science to this. A curiosity, that's very important. Therefore, I really like this kind of studies. But still, do you have any idea how you can make it for application?
Yeah, well, thank you, Takashi. I really don't know why I'm talking at this meeting when I was depressed yesterday. Well, some people like Jane gave me hope because maybe the fisheries are being restored. But yes, really, right, where we do synthetic biology, where we make an evolvable system with 6 or 8 letters in our DNA instead of the 4 that you just have, that has actually having enormous practical application. So if you have hepatitis B or hepatitis C or HIV, it is likely that you will have been diagnosed and had your viral load measured by chemistry that came out of our laboratory, and you would have the pleasure of knowing that a small fraction of what your healthcare provider paid for your personalized medicine came back to our laboratory to support research in basic areas. But yeah, so the ability to have an artificial system with expanded evolutionary capacities, which is what we've generated on the right-hand side of that wedge. And of course, we got a lot of that by the bottom side of the wedge, that is understanding how natural evolution works, which of course is what you specialize in. That was very valuable and very informative for helping us understand how our own systems evolve. That has enormous practical value. But just the statement that, 4.36 billion years ago, life originated is, I don't see, but who knows? I mean, Daniel gave a talk yesterday where the point was made again and again and again that there was something we had no idea what its value was, and it eventually turned out to be very valuable. So let's hope.
Yes. Last question from Stephen Chu.
Yes. Could you comment, there's some controversy on when water appeared on Earth. Yes. The early history, 4.6 billion years ago, most people feel there was no water, but somewhere between 4.3 to 4.0, water appeared. What are your views on that?
There are 4 most important words in science. I do not know. Right, so the Kirschvink, there's a large group of people who say that Earth early on was a water planet covered with Earth, and the argument there is partly water. There was some water on the surface, but there was very little plate tectonics, which means there was very little elevation to get yourself above water. So obviously, if you're a perfect sphere, 1 molecule of water floods the entire planet. So there's this back and forth where we have been denied. The current thinking is to deny us dry land because there's too much water. Now, you've seen the latest papers deep down in the earth. There are reservoirs of water in the minerals, and the current view, and one that I also hold, which is based on the hydrogen deuterium ratios, among other things, in the actual water that we have compared to water from outside, is that we actually think that the most of the water is coming from accretion water from the enstantite meteorites that are arriving early. We still can collect those from the orbit that we have right now, and they're not coming later by comets. And so we tend to be more of a rich water early than a water derived late. So the water is coming available out of the outgassing of the planet somewhere about 4.5, and it's relatively soon after the moon forming event. But that's a bad and good. It's got both sides of it. It's bad because if it floods the planet, we don't get our dry land. And if we don't get our dry land, none of what I just told you has any credence whatsoever.